Hi everyone, welcome back. I'll be honest, I'm not really a football fan, but like millions of people, I really enjoy watching the Lionesses win the Women's Euro 2025. And as I'm sure you know, there is loads of physics in football. This video looks at projectile motion, looking at splitting motion into horizontal and vertical components of velocity, and then using the SUVAT equations to calculate exactly where the ball will be at any time in its trajectory. Enjoy the video. Right, now we come to the thorny topic of projectiles. What I tend to find with my first year physics A-level students is up until this point in the autumn term, they've been coping really well, and then suddenly it all falls to pieces on projectiles. And it is difficult, but the reason it's difficult is because it brings together lots of difficult ideas that you need to understand at the same time. So we're going to start this with a thought experiment, a concept, and you may have seen this demonstrated by your physics teacher. So there's this little bit of apparatus here, it's rather pleasing, a little spring-loaded mechanism. You have two balls, ball bearings. A is just going to be dropped vertically, and B is going to be projected horizontally, constant velocity, but they're at the same height. So the question is, which ball will land first? Now, you may know this intuitively, or you may get stuck at this first point, because the counterintuitive incorrect answer is that B has more energy or more force or something, so it spends longer in the air, and that's just not true. So they both land at the same time, so maybe you knew that, or maybe you intuited it. And the reason why is because they both have a vertical acceleration of 9.81 meters per second squared. They are both falling freely due to gravity vertically. So they both cover that vertical distance in the same time. It just so happens that ball B is also moving horizontally with constant velocity. So it also moves forward as well, but it's falling vertically. So it's this combination of vertical motion and horizontal motion which gives us the actual path of ball B, which is known as a parabola or a parabolic path. So this is the fundamental idea of projectiles, the idea that the components of velocity, horizontal and vertical, are independent of each other. That's a really key idea. We've mentioned that previously in an earlier video. That is fundamental to what we are doing today. So to introduce this and also to recap kinematics in one dimension, which is what we've done in previous videos, we're going to look at a worked example. So this is Beachy Head, near where I live, beautiful walk, really high cliff. Don't get too near the edge, and certainly don't drop anything or throw anything off it. This is very much a thought experiment. So we drop an object off this 150 meter high cliff. So got a few questions. How long will it take to reach the ground? Okay, well, that's just a one-dimensional problem. That's a straightforward problem. We can just use our SUVAT kinematics equations. We know that U vertically is 0. We're trying to find, we know S is 150 meters. We know acceleration vertically is G, 9.81, and we're trying to find the time. Yeah. So importantly here, U is 0, so UT is 0, so that is removed from the formula. Rearrange to make T the subject. We get root 2S over A. Top tip, always rearrange before you substitute, a much better technique. So we put the numbers in and we get 5.53 seconds. That's a long time. So we've got all this time falling vertically. What would be its speed on impact? Again, that's a one-dimensional kinematics problem. We can solve this in a number of ways. I'm going to use V equals U can say T. Vertically, again, U is 0. A and T, well, we know time, we know A, we can work out the velocity, 54.2. Up to this point, we have done nothing new. This is just straightforward, one-dimensional kinematics problems. Right, part C. What about if we'd thrown it horizontally with a velocity of 6.5 meters per second? So now we have our parabolic path. So we have this horizontal motion and also this vertical motion as well, this acceleration. Now that sounds really difficult all of a sudden. However, if we know the time for that it fell vertically, that is exactly the same. So this is the first key concept that students really struggle with. The time is the same. Even though it's moving horizontally, it is still falling the same distance vertically. So we know the time it takes to travel on this parabolic path. Only now it's moving horizontally as well, with a velocity of 6.5 meters per second. We would always ignore air resistance, and that's a reasonable assumption at low velocities. So this becomes a very straightforward calculation. It's just v equals s over t, constant velocity calculation. So s equals v times t. We've made s a subject. We know the velocity horizontally is 6.5. We know the time is the same as it was before, so we can calculate the horizontal distance, which is 35.9. So this is really important. So we can treat the horizontal and vertical components of velocity independently, separately. They're not connected to each other. Very, very important. Right, so let's look at this in a bit more of a complex way. So we're going back to our ball A and ball B example. So they both start here. They're falling a distance, 1.5 meters. Ball A drops vertically. The distance between these balls increases because this is the same time interval. You can imagine this might be a stroboscopic or kind of frame by frame video. Ball B is taking this parabolic path, so it's also moving horizontally. So we're going to consider what are the components of velocity at any particular point. So let's consider the vertical components. So shown by these red arrows, that's our code here. So this is really important. The vertical component right at the start is 0, that's important. U is equal to 0. And then we're accelerating. So after a certain amount of time, the velocity increases and gets larger and larger, and then it's the largest just before impact on the ground. And it's the same for ball A and ball B at any particular point. We can then consider the horizontal component of B. There is no horizontal component of A, and we assume that this stays constant. So we have this constant length blue arrow all the way through this journey. So the actual velocity of ball B is a combination of its horizontal and vertical components, so shown here by the green arrow. So this is where we're going to have to go back to our understanding of Pythagoras and trigonometry, SOHCAHTOA, and we can work out what the resultant is effectively, the actual velocity, the green arrow. And we can see here that not only is that arrow getting longer, which means the ball is getting faster, it's also changing direction. And the reason it's changing direction is because we have this vertical acceleration. So this is why this particular curve, known as a parabola, is the way it is because it's a combination of horizontal constant velocity and vertical increasing velocity. And this is what gives us a parabolic path. So this consideration of how these two components combine together is fundamental to answering projectile questions. So let's look at a worked example. So we've projected a ball with a speed horizontally of 3.5 meters per second. Very good. It says find the speed and the angle to the horizontal of the ball just before its impact. The vertical height is 1.5 meters. Okay, so it's quite useful to consider this analysis that we've just made here. So in order to work out this value x, shown here, this green hypotenuse, I'm going to need the horizontal component. Well, we know that hasn't changed, 3.5. I also need the vertical component. Well, I can calculate that because that's going to be the same as if we had just dropped it vertically. Big conceptual point here. So even though we have a two-dimensional parabolic trajectory, I can calculate the vertical component, this red arrow here, just before impact, just with 1D kinematics. So U is 0, that's really important. Very often students think U is 3.5. Well, vertically, U is 0, as you can see here. The distance is 1.5, the acceleration we know. We're trying to find V. Okay, so V squared equals U squared plus 2AS. Make V the subject. U is 0, really important. We can calculate V, that's the length of this red arrow, is 5.42. So that is the final vertical component of velocity just before impact. But we want the actual velocity, which is the combination of the horizontal and vertical. So then we can consider this triangle. Horizontal component has not changed, that's 3.5 meters per second. The vertical component we have just found, 5.42. So to find the actual velocity is just the hypotenuse of this triangle. So we can use Pythagoras. So the square root of the sum of the squares will give me 6.45. Sounds about right. It's the biggest of the three. And then we're trying to find the angle to the horizontal, which is this one here. I can use sine, cos, or tan at this point. I've decided to use tan. So tan of theta is the opposite, 5.42 divided by adjacent, 3.5, and I can find the angle. So what we're finding here, because we've got a vector quantity, we've got the magnitude, that's the 6.45, and the direction. We always have magnitude and direction. Right, bit more difficult. So up to this point, we've considered things being projected from a height or being thrown off a cliff. So that is from this position 4 here. And that's quite complex, but that's a little bit more intuitive because we can imagine things falling and maybe we can see those more clearly in our eye. What we need to consider now for this full analysis is things being projected from ground level. And this is more difficult for a number of reasons. So imagine, very often this is a sport type analogy. It could be a football that's kicked, or a golf ball, or some other projectile, starting in position 1, going up to its highest point in position 4, and then dropping down to position 7. The first thing to note here is there is symmetry. We have a similarity on the way up and a similarity on the way down. So the horizontal distance of these two sides is the same. The vertical distance must be the same. The time from position 1 to 4 is the same as the time from position 4 to 7. The horizontal component is the same all the way through. That doesn't change. The vertical component is really complicated. So it starts off with an initial maximum value. That's the maximum or the initial vertical component, which we can calculate. And that will decrease, it will get smaller and smaller until it becomes 0. So we're not saying the overall velocity is 0, just the vertical component is 0. And then it starts to fall, it changes direction. So then it gets faster and faster and faster. And we have a bit of similarity here, it's not quite symmetry, but the value of the vertical component velocity in position 1 is the same as the final vertical component over here. Similarly, position 2 and 6, same magnitude, different direction. So this is just as if you've got a ball and thrown it vertically upwards. Its maximum velocity to start with, reduces to 0, and then changes direction, and then comes back down vertically. So now we have this more complex resultant, the green line, is we have this change of direction from an angle all the way to horizontal, and we have 0 vertical component, and then it's going back down to the ground level because of this changing vertical component. So there's a lot going on in this little diagram here, and you really need to think about that and make sure you're clear on it, because we need to be able to understand that to answer our next question, which is our standard projectile question, which you need for the exam. So let's have a look at this. We have an object, a football, projected at 15 meters per second at an angle of 50 degrees to the horizontal. There we go. What is the range? So this is really typical. But this is your kind of standard exam question. How far does this object travel horizontally? And the way we approach this, well, there's a number of ways you could do it, but this is my preferred way, and this is the way that my students tend to understand more clearly. The first step is to find the horizontal and the vertical components of velocity. We must do that. That's always the first step. Even if you cannot answer anything else, you'll get 1 or maybe 2 marks for this. So we can draw a little triangle here. We're going to use SUVAT as we've done in previous videos when we consider components. So the horizontal component is adjacent, so that's cosine, 15 cos 50, that will give you 9.64. The vertical is opposite, that's going to be sine, so 15 sine 50 will give you 11.49. So again, we've got the same color code, so blue is horizontal component, red is the initial vertical component. And importantly, from this point forward, all we will use is the vertical and the horizontal components. We're not going to use 15 meters per second ever again. We don't need that. And that's a common mistake. Very often students go back to using this value at some point, and that's incorrect. So once we have these 2 values, that's all we need to work out anything to do with this projectile motion. So typically, find the total time that the ball is in the air. Okay, again, there's several ways of doing this. This is my preferred method. So once again, we're going to have to consider just the vertical component. Forget about the 9.64. Just imagine that you've got a ball and you've thrown it vertically upwards with an initial velocity of 11.49. So your u value is 11.49, not 15 meters per second. We're just considering one-dimensional vertical motion. We're going to consider how long it takes to get to the highest point. The highest point, we said, the vertical component of velocity is 0. The acceleration is g, but obviously that's acting downwards, so that's minus 9.81. And we're trying to find the time just from the lowest to the highest point, position 1 to position 4. So we rearrange our expression here, make t the subject, stick in the numbers. It's very important you get the v and the u the right way round. So the v is 0, the u is positive, but we're taking it away. So we have minus 11.49 divided by negative 9.81. That's really important. These negative signs cancel, so we get a positive time. Now, negative time is not impossible. There could be a scenario where we have t equals 0 and we're considering a time prior to that. But in this case, a negative time would make no sense. So we must have a positive time. So that's the time from the lowest to the highest point. But we talked about this symmetry earlier on. So the time from the bottom to the top is the same as the time from the top to the bottom. So the total time, nice and simple, we just multiply our previous value by 2. That gives us the total time. Right, the final stage is the easiest stage. If you remember right at the start, we looked at that object being projected off a cliff. If I know the total time is 2.34, and I know the horizontal velocity, once again, this is the value that we use. Very often students go back to the 15 meters per second. At this stage, totally incorrect. That's not a horizontal velocity. I know the total time. I know my constant horizontal velocity. So it's v equals s over t. We step away from the SUVAT kinematics equations. We just make s a subject, v times t, and I just multiply my horizontal component of velocity by the total time, and that will give me 22.6. You must understand this. If you do not understand this, you will, it's a bit harsh to say you won't pass the exam, but you'll really struggle, because this doesn't just apply to mechanics projectiles. This crops up in numerous other places in the course, and it's fundamental. There's lots of stuff going on here. We've got this whole concept of components of velocities, independence of components. We've got trigonometry, we've got Pythagoras, we've got changing directions, positive and negative, lots of stuff going on here. So really, really important you're confident with how to do this. Right, well done. If you understood that, that is a difficult topic, so well done. I recommend the next video is the Physics A-Level Mechanics, Work, Power and Energy, which is on YouTube. As ever, if you want to go to PayHip, Grade A Physics, there's lots of detailed, structured resources there, which I'm sure you will appreciate. Right, any comments or feedback, leave them in the comments section, and see you in the next video. Bye.